In the last episode, we saw how programs end up as binary code for our computer to understand them and to run them. In today's episode, we will review the concept of memory. There's storage memory, which is for persistent data, but today we will be concerned with fast access memory. That's where RAM and registers come into play. I'm sure you've heard about RAM and ROM memory. ROM memory, or read-only memory, stores persistent data such as the BIOS, for example, and it's not that relevant for today's topic. RAM memory, on the other hand, is random access memory. This is a volatile memory which stores data of the programs that are being run at that moment. And that's what we're going to focus on today. So what are registers? We can think of registers as sections in our CPU. So imagine we have our CPU divided into different sections. There are a lot of different registers. Some of them have a specific purpose, but when we program, we generally use general purpose registers. Depending on the architecture of our operating system, we could have 32 bits or 64 or 16 or 8. This is the size of our registers. Depending on the architecture, we have a different size. The smallest chunk of data processed by our processor on a cycle, so you know our processor runs in cycles. In one cycle, the smallest chunk of data that it processes is nominated a word. A word is again linked to our architecture. In different architectures, words are different sizes. It tends to match the actual architecture, but not always. It depends. As a rule of thumb, it does. When we are talking about when we're talking about 32-bit operating systems, they are usually 4 bytes. When we're talking 62, they are 8 bytes, and so on. This would be 2 bytes and 1 byte. But again, this is something that you would have to review or to check. This is a general rule of thumb. This is the most common way. Our operating system, on the other hand, uses what is nominated pages. Pages are resources that our operating system allocates for our program. So pages are usually 4 kilobytes, but in modern systems you can find them from 2 megabytes, and I've even seen them 1 gigabyte pages. This is important because the way it works is we have a program. Our operating system will calculate how much resources our program needs, and it will return pages for our RAM memory. These pages are delivered to us as some addresses, a range of addresses, so we can have something, I'm writing numbers here, but something like from 0F to, let's say, 1B. These are the addresses that our RAM is going to allocate. Not precisely like this. This is actually just our operating system letting our RAM know how much resources are calculated for this program, and our RAM memory will deliver to us, to the CPU, these addresses, which are virtual addresses. These are virtual memory. This is important because the addresses are not for physical memory in the RAM. This virtual memory is mapped to the RAM, but what we are using in our program is actually a virtual memory address. What happens now is that each time we want to allocate something, we will allocate it in the virtual address. For example, here, this would be the last, and it will be allocated here. If we reach a point where our memory is full, we will create what is called a swap. And this will search for the least used pages and swap them to the actual storage in order to liberate or to free some resources for our currently running program. Of course, these resources moved to the disk are still accessible for our programs, but it is a lot slower to access disk storage resources than it is to access our registers or our RAM memory. In fact, the fastest resources we can access would be 1. Registers, 2. Cached content, 3. RAM, and lastly we would have our disk. Okay, so the first thing we need to do is to declare the data. We do that in assembly by doing section data, and here we can type the name of the variable, then declare bytes, and we're going to type hello assembly. And finally we can set the new line character like so. Another variable I'm going to declare is the length of this string. We will need it because we are going to use the write to standard output. Again, all of this I won't go into detail because we will see it in further videos. But for now, just I can show you real quick these syscall tables. We will use the write, and if we go real quick here, we can see that it takes 3 parameters. It takes the file descriptor, it takes the buffer, and the size of the buffer. So the file descriptor is going to be the standard output, the buffer is going to be our string, and the size of our string is what I'm declaring right here. So for that, I'm just gonna go and do EQ. This is usually how you declare constants. And let's do man's message. So this is basically calculating the length of the string. Right. This right here is basically reserving or allocating these resources into the RAM. Then here we will declare the second section, which is the text section. This is the actual code section. We will declare the start. The start is, you can think of the start as the entry point of our program. So we can now start coding the program. The first thing we're going to do here is moving into RAX. RAX is one of the general purpose registers. Let me show you something real quick here. So we're using RAX because we're on a 64-bit system. If we were on a 32, we would be using EAX, or if we were on a 16, we would be using AX, and so on. So the RAX registry, if you come here, you can see the values returned from functions to this register. We're going to load this register with the syscall we want to make. In this case is 1. We can see it here. This is right here. The write function is RAX1. And if you remember, we saw that this takes 3 parameters. The file descriptor, the buffer, and the size count. The file descriptor here, we can see we have the standard input, standard output, and standard error. So we can tell that it is number 1 in the system. So we're going to move this into the first argument. If we come here, we can see here it is. RDI takes the function first argument. So we're going to use RDI and we're going to load it with 1. This is moving write syscall to RAX register, moving setting standard output and then the second argument it takes is the actual string. So we can see here RSI takes the second argument. So we can use move RSI and we're going to load that register with our message. Load message into RSI register. Next we have a third argument, which if we come here we can see that the third argument, for some reason I cannot see it here. but it is this one. It is RDX. It is not specified here, but RDX takes the third argument. So we will do move RDX and we will pass the length. Load the length of string to RDX register. And once we have our write call, our write call and our three arguments here, we can do a syscall. And this would pretty much work, but we need to exit our program so we can free the memory. If not, we will get an error, right? So in this case, what we are going to do is basically use the exit syscall. We are going to load our REX register with 60. This is load exit syscall, and if we come here we can find the exit syscall is number 16. Here it is, and this, you can see, it takes just one argument, which is the status, right? So in this case we are going just to load a 0, which is standard for everything is cool. So load 0 into RPI register and syscall. And this is pretty much our entire program. So as you can see, we are allocating resources in the RAM. The RAM is basically giving us some range of addresses, and we are using our register to perform operations. Once we use the registers to load the syscalls, we call the actual kernel to perform a function or a procedure or a routine. In this case, we're calling the write function and we're calling the exit function. Once we have this program, we can, so here we can use NASM to basically compile our program. We use NASM to compile our program. We will just have to pass the version we're using of 64 and the actual program. Instruction expected at 6. Oh, sorry, I had a typo here. That's the problem. Now we can retry. There we go. And this will create an object file. So if we inspect this, we can see this is basically machine code. And we will use a linker to create an actual executable. And that way we have our hello world executable, and there it is.